Okay, great. Should be recorded. Great. Okay. So originally we just want to have a Taylor's expansion on k omega, which is the refractive index time 2 pi over lambda, right? So that piece caused the pulse broadening, right? So originally here, propagate, it become broaden pulse. Why? Because refractive index is different for different wavelengths. So we want to find how much it is. The Taylor's expansion, we have K naught on the right-hand side. But we want to shift the center frequency, right? We remove the center frequency, carrier frequency. So our pulse is centered at omega equal to 0. So we minus K naught. Because of this minus K naught on the right-hand side is the piece rest of the Taylor's expansion, right? Okay, let me move on. So now, yeah, we can find out, and we find this U bar, right? U bar ZT, right? This U bar ZT is the this U bar ZT is A omega, right? A omega. So this we substitute here. So it is the integral of negative infinity. We take a derivative because omega naught is a constant. So we can d capital omega and d omega is the same, right? So this equation we rewrite divided by 2 pi A bar. Omega minus omega naught will use a new variable, right? New variable. This omega, you can consider that is the omega, right? This is the omega, capital omega. So capital omega is the omega minus omega naught. Then we multiply exponential, yeah, curly bracket, right? I, and then K. So this piece we define as K omega. That's a bunch of items, right? And then omega minus omega naught is capital omega minus capital omega T. Right bracket, curly bracket, right? Okay, so let me read. U bar, you have a question?
Yeah. Should there be a z in the equation after k omega inside this?
Thank you very much. So it's you're exactly right. It's k omega z minus I omega, and there is no I here. I cannot read my notes. Thanks for pointing it out. Great, right? So it's the exponential I bracket k omega z minus omega t. So basically, we do the Fourier transform here. Now we remove the carrier frequency. We only look at the signal without carrier frequency. So we remove this k naught omega, right? Now Fourier transform become here. Everything is now based on the capital omega. Everything is based on the capital omega. And so we are going to take a Fourier transform here, right? Okay, now let's do D. Any questions? Okay, great. Yeah, please feel free to interrupt me. We now derive a propagation equation, right? We want to actually add here, and this once we have this pulse with the k, we want to derive this pulse, right? So let's take a derivative d. So take a derivative on du bar zt, with dz, right? It should be partial derivative, right? It should be partial derivative. We now take a derivative of u with respect to z, so we can propagate in z distance. Equals negative infinity infinity d omega over 2 pi, right? D omega over 2 pi. And this a omega is a function as omega. It's not z dependent here, right? So in frequency, so let's take a derivative. So we have this a bar omega, right? A bar omega. And then we take a derivative here. We have a z, so it is ik omega, right? Ik omega. And then exponential ik omega z minus omega t. This is omega, right? Because I take a derivative, we have a derivative, so the only z-dependent term is this, right? So in other words, when we take a inverse Fourier transform, this a omega stay, the k omega z, we take a derivative, right? Then we move ik omega here, right? So let me ask a question, right? If this k is not omega dependent, in other words, if we have it in the air, in the vacuum, the k is a constant, then this constant will simply move out, right? This k, ik omega will simply move out. Then when we take a propagation, take a derivative, meaning that if we propagate from here to there, if k is a constant, then this integral, the shape does not change. The shape does not change. So if ik omega is not omega dependent, shape doesn't change. But due to the ik omega, k is a function of omega, it's wavelength dependent k, then the pulse will change, right? The shape will change. That's the physical reason why pulse change the shape. It's due to this guy, this bad guy, right? This bad guy caused our problem, right? That's why we are, we're here to study, right? Okay. So what is k omega? What is k omega? Is this. So we will put this piece over here. We will put all this big chunk over here. So then for each term, we take a Fourier transform. Then we will come back to, we'll find out what kind of pulse it is, right? It's kind of long and tedious, but even I can do it. So let's do it together, right? Okay, let's do together a omega, yes. Omega, this d omega, d capital omega over 2 pi. And now let's move a omega later on, but let's do ik omega first. Ik omega is here, so let's copy it, right? Let's copy it. So it's ik naught prime omega plus I over 2 k naught double prime omega square plus 1 over 6 k naught triple prime omega cube plus all the remaining term, and then a bar omega, right? A bar omega, and then exponential, and we'll just copy it down, right? And the exponential I k omega z minus omega t. Will you be able to see it? Kind of, right? Let me read it to you. So this piece equals integrate from negative infinity to infinity, d omega. So d omega over 2 pi, this big chunk is from here, right? This big chunk move to here, right? And then the remaining piece, exponential I k omega z minus omega t, copies, right? Exponential I k omega t, this should be t, this should be z, I k omega z minus omega t. So it's just copy. Apologize, it's in the corner, but you should be able to see it, right? Questions? Okay, so we will just take the Fourier transform of this piece, right? So let me keep the last equation and then move, take the further steps. It's a lot of derivation, but let's do it together, right? Let's do it together. Okay. Okay. Now let's take a derivative with respect to t also, right? Okay, so let's take a derivative with respect to k, right? Partial, we did u zt, right? So now let's do u zt with respect to t, right? And then we add k naught prime. So we add the k naught prime, right? We add the k naught prime. So why don't we spend 30 seconds? Why don't you write it down? What is the let's add a negative here. How much it is? So you already have u zt from the previous equation. Take a derivative with respect to t and add negative t naught, k naught prime. Okay, so can anyone tell us what is the right hand side of this equation?
The integral from negative to positive infinity, d omega over 2 pi, a bar omega, I omega negative k naught.
So we have negative, yes.
And times exponent I k omega z minus omega t. And k omega z and also in parentheses, yeah.
Yeah, k omega. So my omega, I didn't write it in a very nice way, right? Okay, right? Okay, now let's add a, let me add a negative sign, right? Negative sign, so this become positive, right? This become positive. Okay. Okay, great. So that's very good. So if you compare this equation and this equation, so if you compare this equation and this equation, you will find out that this piece, right? This piece and this piece, they're the same, right? So if I take a derivative with respect to z, it will be the same as the as several pieces. And the first piece is the derivative with respect to t, because we are only, I want to have the I omega, I capital omega. So I got I capital omega, right? So now we can write as du dz as a du dt, du dz as du dt, right? So now we can take a propagation. So this is basically a propagation. This is time derivative. So if I have a pulse, I'm able to calculate the time derivative. Once we get the time derivative, I'm able to propagate, right? As to how to propagate, we will learn eventually, we'll learn later. But at least we can write as this equation, right? So we can write as this as the du dz du partial u with respect to z as a function of du dt, right? Partial u partial t. But how to deal with the second term? Any idea? So this term comes from the partial u z t partial t. So what is this term? Can we, any idea how to find this term?
Would it be the second derivative with respect to time?
That's very good, right? Because we have the omega square, let's write this as a du dt zt second derivative, right? And then we can get this as a third derivative, u z t, right? T square. So now we can write this the partial u partial z as a equation of partial u partial t partial u partial t square partial u partial t cube, right? Third order, right? Okay, so let me write it again. So this will be the k, right? K naught prime partial u partial t square square second order, right? So equals, now let's do this as a positive, right? So this will be the negative also, right? But let's actually write together negative infinity infinity the capital omega over 2 pi a bar omega. So let's do k naught prime I omega square exponential I k omega z k omega z minus omega t, right? So that's this piece. So now we have omega square, right? We have a I here, right? So I square will be negative, right? So let's now put a negative here. Remove the I, right? Remove the I, and then have a half, and then let's add a half, right? I over 2, let's add an I. So I add extra term, so the right-hand side matches the second term here. I add extra I, negative I over 2, so now I square is gone. I here over 2, so matches the whole thing, matches the second term. And I can do the third term also. All together, we can, so this is the third term I'm going to skip. So we get, right? So we get left-hand side partial u zt. This is partial z, right? This is a bar equals the first term is this, right? So negative k naught prime partial u partial t zt. This is bar. Second term minus I, right? Partial term minus I, and then we have k naught over 2, but this should be double prime, right? So double prime. I actually missed that. This should be double prime. This should be double prime. This should be double prime. So double prime partial u partial t zt, right? And then we will add the third term plus 1/6. It's 3 factorial, right? K naught, I'm just directly writing it down. Partial u partial t bar zt, right? Third order derivative. And then we should write all the way down to the infinity to be complete. But for our calculation, if we know the remaining term is smaller and smaller, we can just write down with 3 terms, right? Okay, so this is actually our propagation equation. This is actually our propagation equation. Right? Okay, questions? It's actually, so remaining of the class will deal with this equation, right? How to solve this equation.
Dr. Who?
Yes?
Would there be a minus sign in front of the 1/6k triple prime?
Oh, okay. Yeah, thanks for asking. So let's actually, how about let's do it together, right? Let's do it together. So partial u over partial t cube u z t, right? So let's do it together. It's negative infinity. The third derivative, d omega over 2 pi a bar omega, and then we need a k naught triple prime, right? And then I capital omega third order, right? Third order, an exponential big chunk. I'm going to skip, right? A big chunk. Okay, now we have an I here, right? So we have an I here. So let's remove the I, right? So let's remove the I. So this will be negative I. I cube is negative I, right? But since I want to be positive, this is negative I. Let's move to the left-hand side. It is I, right? Right? So originally it should be negative I because it's I cube. Now I remove the negative I, move to the left-hand side. It's the positive I. And then in order to have the k naught cube, so I need to have k naught cube on the left-hand side. And in order to have the 1/6, let's 1/6. So we have here, it should be over 6. Right? Okay, so now this is the term here. So we need to add this term. So it's 1/6, and there is an I missing. Do I have an I missing? Let me see. Do I have a I missing? Let's hold on. So this will be the I. Yeah. Okay. Because I do have an I missing here. So there's an I here. So I should appear I here, I and I. The remaining is k capital omega. So we have cap k naught, omega square, omega cube, but there should be an I here, right? So there's an I here, there's an I here. So we will add together. This piece is here, and it is due to this term. Thanks for asking. Does that answer your question?
Yes, it does.
Great. Okay, yes. So that's good. It's actually kind of complicated equation, right? But let's be slow. Let's be slow and step by step, right? Let's do step by step, and we can do it together, right? So we do 1, 2, 3 all together. We come with this propagation equation, right? So if you are okay, let me remove all this equation, and that we will have this remaining, right? So we will deal with this equation. Okay, so yeah, and we'll work through those equations, understand by MATLAB. But for now, let's derive, right? So please bear with me. Okay, so now let's all write into the left-hand side, all move to the together. So we can just partial u bar the t with respect to z, and then plus, and let's add an I, right? Plus I k naught prime, partial u, partial t, zt, right? Partial u, partial t, and then we will move negative, so it's become positive, and then we add a I, so it's negative half, not double prime. I just add an I. Okay, and partial u zt with respect to t. Okay, square minus 1/6 k naught triple prime I, and then partial u, partial u, partial t cube zt plus all the way down, right? So I just move the right-hand side to the left-hand side, add an I, right? Positive times I, this will be positive I times I, so it's negative. So there is no I, it's negative times I. That's the equation, right? All the way, add all the term to be 0, right? So it's just, we'll just deal with everything on the left-hand side.
Excuse me, I'm noticing some use our bar while some are not. Is that supposed to be?
Yes, thank you. So those are all should be bars. Thanks for pointing it out.
I also have a question.
Yes.
When we derived the last equation, we ended up getting, like, the part that's circled in red right now, we got I/6 times k triple prime, but you just have 1/6 written there. So when you add in the second I on the next line, wouldn't the I's cancel out?
There is no I here, actually. It's just 1/6.
Okay, yeah. We just know, just before what you erased, though, you had I/6 written there. There is no I?
Yeah, there's no I.
Okay.
Yeah, I can go over with you, afterwards. So if you feel like there is an I, we can talk later on.
All right, that's great.
Okay, so we got that, and then yeah, please go over the derivation. It's kind of it's kind of fun. So and make sure everything's correct. So there's no there's one, there's no I. Okay. Okay. Now let's drop in the bar, right? Now we write as the U. So and then let's drop the bar, right? Drop the bar. So use U the T to UZT. Right? So now from now on, I'm going to drop the bar and use the UZT to represent U bar ZT. So you can consider as we are still used it to a shifted, right? So remember we shift the, right? Remember we shift the frequency, remove the carrier frequency, right? So U bar represent the one without with shift frequency. But now for the simplicity, we don't want to write the bar, because I'm lazy. So we don't want to write the bar each time. So we are going to use U to represent U bar. If you want, you can consider this as W, right? Use W to represent the U bar. But for the simplicity, let's still use U. Let's still use U. Let's drop the bar, right? Okay. Now let's look at it. If we have, right? If we have that as, if we don't have this K double prime, K triple prime, if we don't have that, assume, let me do this, right? If we don't have this, right? If we don't have this, if the K double prime, K triple prime is 0, what we have is this equation, right? Partial U, partial Z, ZT, plus K naught prime, partial U, partial T, ZT, right? This equals 0. Is this equation sounds like familiar? To any of you? So du dz is K naught du dt. This equation is called propagation equation, right? So this equation actually represents wave propagation. This represents the wave propagation without change of shape. Right? So if you were in my optics class, you will learn that actually du dz plus K naught prime du dt is 0. It's actually the wave propagation. And what is Vg is 1 over K naught prime is the group velocity. The group velocity, right? That's how this pulse propagate, right? So I have a pulse and then, propagate. So this is the Z and propagate, right? So that this equation characterize the wave propagation equation, right? Wave propagation equation. If I have an example, I'll show you next time. So let me make a mark. And if I have an example, I'll show you why this is the propagation, right? Okay, so but this is the group velocity. So this is the propagation, this is the group velocity. So assuming that all the K naught double prime, K naught is 0, it's negligible. So that piece will have no contribution. Then this is the pulse propagation without change of the shape. I write it in a bad way, a change of shape, but it shouldn't change the shape. But due to the contribution from here, it will change the shape, right? So now with those terms, with those high order terms, The pulse is broaden, 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 right? Broaden, broaden, and then we will study those terms, in our class, right? Okay. Questions so far?
What happened to the I's that were on the higher order, or sorry, the lower order terms? So the
You mean
D,
this?
yeah, that one and the
Oh.
one before.
Yeah, the I just, because I didn't include those terms, it should be have an I, but since there's no, since I only consider two terms, I just drop it out.
Okay.
Yeah, thanks for asking. Yeah, it's good. I mean, it's good to have some discussion, right? It's good to, I mean, since chances are, I always talk to my student, if you have question, chances are that your classmates have the same question, right? And then if you ask, you're doing a favor for your classmate, right? Okay, so I'll try, keep in mind, I'll try to actually explain why this is the simple propagation equation. But the bad guy is those two, right? The bad guy are those. Due to those bad guys, it propagates broadening, right? It broadening. Okay, now we can keep this equation, right? Keep this equation, okay? And keep, oh yeah, I erased it, but that's fine. Okay, so now we can subtract group it. So it actually, this propagates, right? But what we want is that in time domain, where this propagate, I don't want to see the change. So let's say we now subtract E, we now subtract the group velocity motion. The group velocity motion. We now subtract group velocity motion, meaning that it's actually propagate, right? But in my screen, I don't want to see it propagates. I want this stay as, in my monitor, right? In my code, I want this to stay. But let me assume I know as time goes, like past 1 second, it's actually, I know it's propagate with the speed. But what I only care is how much the shift with respect to this group velocity, right? So how much is the shift with respect to this group velocity, right? 1 over k naught is the group velocity. So now I'm going to change to a t prime, change a variable, right? So we now change a variable equals to t minus k naught prime z. What is k naught prime? Is 1 over velocity, right? So this is the group velocity. So it's 1 over v, 1 over z, z divided by v is the time. So it's the elapsed time. It's the shifted time, right? So this t is a shifted t. This t is a shifted t. Okay, and z prime is equal to z. So now we are going to shift my time domain and the z. Time domain and time shifted by amount of delay, right? Elapsed. And the z is the distance, right? Z is the distance. So now we are going to have it, put it here, this equation, right? This equation. So let's do I partial u z, right? Z prime. So now t minus t naught z, right? So okay, with respect to the t, right? So let's now with respect to t, now I use the t prime, right? I use the t prime. And then this equals, we use the chain rule, right? So let's use the chain rule. What is this chain rule, right? Multi-variable chain rule. So it's this is the chain rule, right? chain rule, the partial u with respect to z equals partial u with respect to x, partial u with respect to x, partial u, right? Plus partial u with respect to y, and partial y with respect to z. If u is a function of x and y, when we take a partial derivative with z, we need to include the chain rule, right? Include the partial u, partial x, partial z, plus partial u over partial y over partial z. So with that case, we need to put it here as the z. Actually, it's the z prime, sorry, z prime, right? Okay, now let's take a look. So this z prime is I partial u z prime, and then with respect to the t minus k naught z, right? But let me write as the u over z. U over z. So this is I'm representing as the derivative with respect to z prime, right? So I'm actually writing my notation with this d partial u partial z prime. And then we can add another term, right? And another term as u with respect to the z also, right? So minus, this should be minus, right? I'm actually minus and u, right? So it's partial u, partial z t prime, and partial t prime, and partial t prime over partial z prime, right? So basically it is, yeah, let me write it with respect to here is the partial z prime, right? So I take a first derivative, so partial u, partial x, it's just the z prime. And then minus with respect to the t, right? T prime, t prime, t prime, and over z, right? But now, if I can ask, we will simply, no, excuse me, this will be the I, right? I u z prime t minus k naught z over z square. It's the same thing, but here, when we take a partial derivative of u prime over z, it's negative k, right? So it's negative k. So this is minus k naught prime times I, right? Times I, and the partial u z t partial t prime, right? Partial prime. This piece give us the negative k naught. This piece give us the negative k naught, right? And now when we
excuse
come
me.
back, yeah, go ahead.
Just to confirm, that first term is u, not du?
You say it again. This time, are you talking about this term? Hello?
You say it's supposed to be u and not du?
Oh, yes.
Okay, thank you.
Okay, great. So this is the, yeah, thank you. I should have this also, right? Okay, so partial u and then partial z prime, right? And then we have k now partial u, partial t prime. Okay, now we use the chain rule, right? So with this, we will substitute move here, right? We will move here, and then what we will have is I drop the bar, right? Remember I dropped the bar, z, t. So this will be t prime, right? T minus k naught prime. This is prime. And this will be t prime with respect to the t z prime. With respect to z prime. And then minus ik, right? So this will be minus ik naught prime, partial u, partial t prime, zt prime. And then we add this term plus ik naught prime, partial u bar, partial t prime. So I just changed the time. We'll just shift the time, t prime, right? We'll just shift amount of time, right? Okay, because when I actually take a derivative with respect to the t, the z is a constant, right? Z is constant here. When I take a derivative with respect to t, z is a constant, so dt prime is dt, right? dt prime is dt. Okay, then, and let me finish. Is that a negative? Yeah. Negative I over 6 k naught triple prime, partial u bar, partial t cube, and then z, let me write it more clearly, t equals 0, plus all the remaining term, right? Let me first check my equation, whether that's correct, minus, and there is no k, there is no I here, right? The dropping the bar, that's the, oh, it is I, sorry. It is I here, and minus, did I miss? Oh, yeah, I had something wrong. So I'll just copy it, right? Minus half k naught double prime, partial u, partial t square, dt minus I over 6 k naught triple prime, partial u, partial t cube, zt equals 0. Of course, we add more terms. Let me check. Okay, that's correct. So I'll let you write it down, and then I will go through this equation again. Okay, okay. So that's the, I'll let me explain this equation again. So this is our original equation. This part, I'm going to change the t, shift t by k, shift t by to k naught prime z, right? So instead of the time varies, right? What we want is a shifted time. So I change to t minus k naught z. So in the end, use the chain rule, we got two terms. Because of these two terms, we write it in here, and we just copy the remaining term here, right? That's it. Any questions? Or did I, lost you? Okay, so that's fine. And you can find out these two, they are the same. They are the same and they should cancel out. In other words, once I shifted, right, shifted time, this partial u, partial z should be 0. Should be 0 if we don't consider the remaining term, right? If we don't consider remaining term in this equation, we should be all actually equal to 0. This will be equal to 0. So now what we have is that the change variable drop the prime, and then we will change the variable and drop the prime. Change variable and drop the prime. This is what we got. Change variable and drop the prime. So what we have is I partial u partial z zt minus half, and we'll copy from here, k naught double prime partial u partial t square u square zt, and this square should be on the right hand side, minus 1/6 I/6 k naught triple prime partial u partial t cube zt equal and all other terms, all the other terms equal to 0, right? So these two, they cancel out, and we only have this propagation term, this k double prime term, k triple prime term. If we don't have the k double prime and k triple prime, du dz will be 0, meaning that our pulse does not change any shape, right? Our pulse does not change any shape, okay? Questions? Or you guys are totally lost? Or you're okay? Okay, so let's look at other convention. So we will have the other convention, right? So this is the convention. We use the physics convention, and we derive this propagation equation, and we will work together to study how to solve that, right? And this is the physics convention. I'll finish this two convention, and then we're done today. Physics convention, right? Physics convention is I partial u partial z, right?
Excuse me, you're saying physics convention, but you're writing out mathematics. Which is
Thank
it?
you. Thanks for correct me. So yeah, it's a mathematics convention. This is the physics convention. Thanks for correct me. And this is the mathematics convention. Yes, you are correct. Partial u partial z. Yes, minus 1/2. When I write the mathematics convention, I always think about physics convention. So k naught triple prime. This is not mean to trick you. So partial t square and zt, right? And then plus 1/6 I/6 k naught triple prime partial u partial t cube and cube zt plus all the way down to the 0. Okay, So it's actually deriving, it's kind of long, right? It's kind of long. So we have the negative the same, but here we have a positive negative, right? Because it's a complicated derivation, and you find out that actually it's only change is the plus sign. And then we have the engineering convention, right? The engineering convention. So this is ENGIN, engineering convention, right? Engineering convention. So in this case, we use J, right? Engineering use J, partial U, partial Z, ZT, ZT, and then we have the plus half beta naught double prime partial U, bear with me, and then we have the ZT minus J beta naught cube divided by 6 partial U cube ZT with respect to T cube plus all the way down to the 0. So in engineering convention, people usually write beta, but you can consider this beta and K, they're the same, right? Beta naught and K, beta naught triple prime and K naught triple prime. But actually, due to the sign change, K double triple naught and the K triple, beta naught triple prime and K naught triple prime, they have an inverse sign, right? But that's a secondary issue. But in engineering, we use K, we use beta. Use beta naught in engineering convention. Use beta naught. Actually, it's the K naught for so in the over the mathematics and the physics convention, they use K naught, but in engineering convention, they use the beta naught. Beta do the same definition. Beta omega is n omega, right? Omega over c. So it's just the different definition for engineering convention. Okay, more questions? Okay, so it is just a lot of mathematics. It's the way how you calculate wave propagation. So if you have questions, let me know. I can go over with you more. But mainly, we'll just go through the derivation, derive the governing equation, right? Governing equation. You will ask, this is the integrated photonics class. Do we require derivation in the exam? So this is not required for you to go through the derivation. However, we probably do a simple derivation. In other words, it's more like if you understand the homework, you should be fine. But let's do it together in the homework. So this kind of derivation is not required for the exam. Questions?
Could we consider beta naught to actually be negative K naught? Because it's the opposite sign between the mathematics and the engineering.
Beta naught, actually, it is the it's not considered as the K naught. It's actually the same. However, the beta triple prime it has the opposite sign. If you get into the detail, we will learn it together later on when we actually use MATLAB to plot once you put the beta 3, they are negative, how would you change? So beta is actually the same. Because, hold on. Beta naught, let me use the mathematics. Yeah, so let me look at it. You have an interesting question. So we use the propagation. Yeah, okay. Because the definition, right? Definition is actually this definition. We cannot define omega or n as negative number, right? Omega n as negative number. But when you look at the axis, right? So for example, we have the z, and then the propagate on towards right, then this k is the towards right. But when you physically the pulse propagating towards left, right? And we can say, this is the positive z, right? So z axis could be different, but the absolute value of beta cannot be a negative because we cannot have the negative refractive index, except nowadays metamaterial, we have the negative refractive index. But for our context, we won't actually deal with negative propagation constant. But you can, because of the different convention, you are absolutely right. That's a good point. But you can consider pointing into the left as the positive z or negative z. So it's just the way how you quantify, right? Yeah, thanks for asking. But the beta is positive.
All right, thank you.
Great. Those are good questions. I mean, you guys asking good questions, actually. Yeah, more questions? Okay, so we'll stop here, and we derive this equation. The derivation of this is not the focus of our class. We are more like engineering class, right? But I want you to understand this equation. Once we have this equation, what's the physical meaning on k double prime will impact how pulse propagate. Those are the one we're going to learn here, right? How would this k triple prime act on our pulse, right? Those are the one. We're going to use MATLAB to understand those physics. We're more focused on the engineering problem, the physical meaning instead of derivation, right? But we have to, I would like to get through, for me, I'm in electrical engineering, I would like to understand what is this equation from, how you derive this equation, right? I mean, I would like to understand what comes to here, but those are not required for our exam. I would like to focus on how this equation impacts the pulse propagation. Okay, great. If there's no further questions, that's all for today's class, and I'll see you on Monday. Thank you for being here. Okay, bye.
Thanks, Dr. Hill. Bye.
Thank you. Bye.